Welcome to a major new module, NumPy, short for Numerical Python. If you plan to work in data science, machine learning, or scientific computing, NumPy is the foundational library you must master. It provides the essential tool for high-performance numerical operations, the n-dimensional array. 1. What is NumPy? NumPy is the fundamental package for scientific computing in Python. It centers around a powerful data structure called the ND array, which stands for n-dimensional array. This is a grid of values, all of the same type, indexed by a tuple of non-negative integers. It is the core data structure used by most other scientific Python libraries like pandas and scikit-learn. Before importing NumPy, you must install it. You open your terminal and run this command. 2. NumPy array versus Python list. While Python lists can hold various data types, NumPy arrays are homogeneous. They hold only one data type. This uniformity is key to NumPy's speed. Lists store pointers to objects scattered in memory, requiring Python to dereference them one by one. NumPy arrays, however, store data contiguously and use optimized, precompiled C code for operations, resulting in orders of magnitude faster execution, especially for vectorization operations like multiplying every element by 2. 3. The import convention. The standard convention when importing NumPy is to alias it as npy. You will see this abbreviation used everywhere in the scientific Python ecosystem. Always follow this convention to make your code immediately understandable to other data professionals. To summarize, NumPy is essential for speed and efficiency in numerical work. Our next lecture 35.02, NumPy in action. See you there. Welcome back. Having learned why NumPy is crucial, it's time to start working with its core data structure, the ND array. In this lecture, we will cover the most common ways to create arrays, including initialization from Python lists, and using convenient methods to create arrays of zeros or ones. 1. Creating arrays from Python lists. The most common way to get started is by converting an existing Python list or a list of lists into an ND array using the np.array function. Note that a list of lists naturally creates a two-dimensional array, which is NumPy's way of representing a matrix. 2. Initialization methods. NumPy offers specialized functions for quick initialization. np.zeros and np.ones are used to create arrays filled with zeros or ones, respectively, which is useful for reserving space or initializing weights in models. The shape is always specified as a tuple. The np.arrange function works just like Python's range, but returns an ND array, making it ideal for creating sequences of numbers. 3. Element-wise operations. The key benefit of NumPy is vectorization. When you perform an arithmetic operation like addition or multiplication on two arrays, NumPy applies the operation element by element, or to all elements simultaneously in the case of multiplication by a scalar. This behavior is fundamentally different from Python lists, where the plus sign would concatenate the lists. Even comparison operators work element-wise, returning a Boolean array. To summarize, you now know the primary ways to create and perform basic operations on NumPy arrays. Our next lecture 35.03, linespace, logspace, and more. See you there. Welcome back. While np.arrange is useful for simple integer sequences, scientific applications often require generating sequences with a specific number of points, spaced evenly or logarithmically. In this lecture, we explore the specialized NumPy functions, linespace, logspace, and random.rand for these advanced array creation tasks. 1. np.linespace. This function is essential for plotting and modeling. It takes a starting value, a stopping value, and the exact number of samples you want to generate. The samples are evenly or linearly spaced between the start and stop points, including both ends by default. You can exclude the stop value by setting the endpoint argument to false. 2. np.logspace. This function is used when you need points evenly distributed on a logarithmic scale, often for frequency analysis or financial modeling. Instead of specifying the start and stop values directly, you provide the exponents of the base, which defaults to 10. For example, logspace 0, 3, 4 generates 4 points from 10 to the power of 0 up to 10 to the power of 3. You can also change the base, for instance, to base 2. 3. Random array generation. The np.random submodule is essential for simulations and machine learning initialization. np.random.rand generates random floating point numbers in the range 0 to 1. np.random.randint generates random integers. Notice that for two-dimensional arrays, we specify the shape using the size argument and a tuple. To summarize, these functions give you fine-grained control over how you generate numerical data for analysis. Our next lecture 35.04, Using Math Functions. See you there. Welcome back. One of the biggest advantages of NumPy is its collection of universal functions, or ufuncs. These are vectorized wrappers around C functions that allow you to apply mathematical operations to every single element in an array without using explicit Python loops. This lecture will demonstrate how to use common ufuncs for trigonometry, logarithms, and exponentiation. 1. Standard mathematical operations. Many standard math functions are available directly through NumPy. The benefit is that when you call np.sqrt on an array, it calculates the square root of every element simultaneously and returns a new array with the results. This is significantly faster than writing a list comprehension in Python to do the same task. 2. Trigonometric and logarithmic ufuncs. NumPy provides a complete set of trigonometric functions like np.sine, np.cosine, and np.tan. Similarly, for logarithms, np.log calculates the natural logarithm, and np.log10 calculates the base 10 logarithm. All these functions operate element-wise. For example, to plot a sine wave, you can generate a linespace array and directly calculate its sine values with one line of code. 3. Aggregation functions. Beyond element-wise operations, NumPy provides powerful aggregation functions. Functions like np.sum and np.min calculate a single scalar result from the entire array. Most aggregation functions are also available as methods directly on the array object, such as ar.mean, which is often the more convenient syntax. To summarize, U-functs are the foundation of NumPy's speed. Our next lecture 35.05, Array Comparison. See you there. Welcome back. In Python programming, checking conditions is fundamental. In NumPy, when you use standard comparison operators, the operation is automatically vectorized, meaning the comparison happens element-wise. This lecture will show you how to leverage these element-wise comparisons to create powerful Boolean arrays, which are essential for filtering data. 1. Element-wise comparison operators. When you use operators like greater than, less than, or equal to on a NumPy array, it returns a new array of the exact same size, but filled with Boolean values, true or false. The first example compares every element to the scalar 35. The second example performs an element-by-element comparison between two arrays of the same shape, returning true only where the values match. Two. Boolean indexing or filtering. The power of these Boolean arrays is revealed when you use them as indices to select elements from the original array. This technique is called Boolean indexing or masking. NumPy returns only the elements from the original array where the corresponding value in the Boolean mask is true. This is an extremely common, fast, and idiomatic way to filter data in Python. 3. Combining comparison conditions. To combine multiple conditions, you must use the element-wise logical operators, the ampersand for and, the vertical bar for or, and the tilde for not. Critically, you must wrap each individual comparison in parentheses because of Python's operator precedence. This example filters for values that are greater than 20 and less than 50, extracting the elements 30 and 40. To summarize, Boolean indexing is a cornerstone of data analysis in NumPy. Next, we explore other comparison functions. Our next lecture 35.06, More Comparison Functions. See you there. Welcome back. In the previous lecture, we learned how to create Boolean masks using comparison operators. In this lecture, we will explore specialized NumPy functions that aggregate these Boolean results or provide conditional element selection, giving you more robust control over your data filtering. 1. Aggregate Boolean results. After creating a Boolean mask, you often need to summarize the result. The all function checks if every single element in the resulting Boolean array is true. The any function checks if at least one element is true. These methods are commonly chained directly onto the comparison operation itself. 2. Conditional selection. The np.where function is NumPy's vectorized equivalent of a ternary conditional operator or an if-else statement. It takes three arguments: a condition, the value to insert if the condition is true, and the value to insert if the condition is false. Here, we replace values greater than 25 with the string high, and the rest with low. If you only pass the condition, np.where returns the indices of the elements that meet the condition. 3. Floating point tolerance. Due to the inherent nature of floating point arithmetic, checking exact equality between floating point numbers often fails unexpectedly. The np.isClose function solves this. It checks if two arrays or values are equal within a specified tolerance, which is the standard practice for comparing floating point numbers in scientific computing. Always use np is close instead of the double equal sign when dealing with floats. To summarize, these specialized functions give you complete control over conditional logic in large arrays. Next, we will discuss an important topic: copying arrays. Our next lecture 35.07, Copying Arrays. See you there. Welcome back. When working with NumPy arrays, understanding how they are copied is crucial, as arrays behave differently from standard Python objects. This difference can lead to subtle bugs if you are not careful. This lecture will clarify the distinction between a view of an array, which shares data, and a copy, which is independent. 1. Views. A view is a new array object that refers to the data of the original array. This happens when you perform slicing, which we will cover in the next lecture, or when assigning arrays to a new variable without an explicit copy. If you modify the view, you modify the original array, and vice versa. This behavior is optimized for performance, as it avoids duplicating large amounts of data. In this example, changing array B also changes array A. 2. Creating a true copy. When you need a completely independent array, you must explicitly use the copy method. A true copy duplicates the array's data in memory, meaning any modifications made to the copy will not affect the original array, and vice versa. Use copy whenever you intend to modify the new array and must preserve the original. 3. The base attribute. You can programmatically check whether an array is a view or a true copy using the base attribute. If an array owns its data, like the original array or a true copy, base will be none. If it is a view, .base will refer back to the original array from which it was sliced or created. This is a handy debugging tool. To summarize, always be intentional about whether you need a view or a true copy. Our next lecture 35.08, Slicing. See you there. Welcome back. Slicing is a powerful and frequently used feature in NumPy, allowing you to select and modify subarrays. It works similarly to slicing Python lists, but with the crucial difference we discussed earlier. Slicing a NumPy array creates a view, not a copy. This lecture will cover standard slicing syntax for one-dimensional arrays. 1. Basic slicing syntax. Slicing uses the familiar Python list syntax: start: stop: step. The stop index is always exclusive. In the first example, we select indices 2, 3, and 4. Omitting the start index defaults to 0, and omitting the stop index defaults to the end of the array. 2. Using the step argument. The third argument in the slicing notation determines the step size. Using a step of 2 selects every other element. A common trick is using a step of -1, ::1, which efficiently reverses the entire array. 3. Slicing creates a view. As a final note, remember the critical distinction. Slicing generates a view. If you assign new values to the slice portion, the corresponding elements in the original array are modified because they share the same memory. If you need an independent copy, you must explicitly chain the copy method after the slice, like array start::stop.copy. To summarize, slicing is efficient but requires caution regarding data sharing. Our next lecture 35.09, Multidimensional Arrays. See you there. Welcome back. While one-dimensional arrays are useful, the true power of NumPy lies in its ability to efficiently handle multidimensional arrays, most commonly two-dimensional arrays, or matrices. This lecture will show you how to index and slice these higher-dimensional structures. 1. Creating 2D arrays. A 2D array is typically created from a list of lists, where each inner list represents a row. We call this structure a matrix. The order of dimensions is important. Rows come first, then columns. The .ndim attribute confirms the number of dimensions, which is 2 for a matrix. 2. Indexing 2D arrays. To access a single element, you use a single pair of square brackets, containing the row index and the column index, separated by a comma. This is the preferred way. Matrix square bracket row index, comma, column index square bracket. If you only provide the first index, NumPy returns the entire corresponding row. 3. Slicing 2D arrays. Slicing works by applying slicing notation to both the row and column dimensions, separated by a comma. The ::: alone acts as a wildcard, selecting everything in that dimension. In the first example, we select rows up to index 2 and all columns. In the second, we select all rows and only the column at index 1. Remember, all these slicing operations also create views, sharing memory with the original matrix. To summarize, mastering comma-separated indexing and slicing is vital for manipulating matrices in data science. Our next lecture 35.10. Few more attributes. See you there. Welcome back. To work effectively with NumPy arrays, you need to be able to quickly inspect their key characteristics. NumPy arrays provide several attributes, properties of the object, that tell you about their dimensions, data type, and total size. In this lecture, we will cover the most frequently used attributes. 1. The .shape attribute. The .shape attribute returns a tuple of integers indicating the size of the array in each dimension. This is perhaps the most important attribute. For a 1D array, it returns a single number followed by a comma. For a 2D array, it returns the number of rows followed by the number of columns. Understanding the shape is vital before performing operations like matrix multiplication. 2. The .type attribute. Since NumPy arrays are homogeneous, the .dtype attribute tells you the data type of the elements stored in the array. This is often int64, 4 integers, or float64, 4 floating point numbers. NumPy uses fixed size types for efficiency. Checking the dtype is crucial, as the type affects how operations are performed and how much memory the array consumes. Three, the size and ndim attributes. The size attribute returns the total number of elements in the array, the product of the numbers in the shape tuple. The ndim attribute, which we saw earlier, explicitly returns the number of dimensions, which is equivalent to the length of the shape tuple. For our 2x5 array, the size is 10 and the number of dimensions is 2. To summarize, these attributes provide the essential metadata for your NumPy arrays. Next, we will cover some final useful functions before moving on. Our next lecture 35.11. Few more functions. See you there. Congratulations on reaching the final lecture of our NumPy module. We'll conclude by covering 3 essential utility functions: sorting array elements, reshaping an array into a new structure, and flattening a multidimensional array back into one dimension. These functions are frequently used in data preparation pipelines. 1. Sorting arrays. The np.sort function returns a sorted version of the input array. It is important to note that, unlike Python's list.sort method, np.sort does not modify the original array in place. It returns a new sorted copy. This behavior helps maintain data integrity during complex analysis. 2. Reshaping arrays. The reshape method changes the shape of an array without changing its data. It is crucial for preparing data for machine learning models, which often require specific input shapes. The total number of elements must remain the same, 12 in this case. You can use -1 as one of the dimensions. NumPy will automatically calculate the size of that dimension based on the total number of elements. Reshaping creates a view, sharing data with the original array. 3. Flattening arrays. The Revel method is used to flatten a multidimensional array into a one-dimensional array. This is often necessary before feeding data into a linear model. Like reshape, Revel generally returns a view of the original array for efficiency. If you need a guaranteed independent copy, use the similar method flat, which explicitly forces a copy to be made. To summarize, these functions complete your toolkit for manipulating numerical data efficiently. We are now ready to move on to the powerful data structure library, Pandas. Our next module begins with lecture 36.01, Introduction to Pandas. See you there.